Alright, in this video we're going to talk about Unit 5, Objective 3, Limits at Infinity. So when you see the limit as x approaches infinity of f of x, or the limit as x approaches negative infinity of f of x, we're asked to look at what's happening at the far ends of the function. And that should make sense, because if x approaches infinity, that means we're going way over in this direction over here. And if x is negative infinity, we're going way over here. And we're asked to find what y value, right? That's the limit. What y value are we getting close to as we get way over to the right or way over to the left? So that's what this thing means. Now, in pre-cal and in Algebra 2, we called this the end behavior. And part of end behavior included horizontal asymptotes. And if you notice down here, the definition of a horizontal asymptote is exactly this up here. So the line y equals L is a horizontal asymptote of the graph of f of x if the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches infinity of f of x equals L. So if one of these things is equal to some number, if we can find the limit as we go to the far ends of the graph, that's going to be a horizontal asymptote. Sometimes, if our graph like x squared goes up like this, our limit's going to be infinity, or it's not going to exist depending on which way you want to think about it. So we're not going to have a horizontal asymptote. But if we have a function that goes like this and kind of flattens out, we're going to end up finding the limit at that y value. So the limit's going to be approaching that y value. That's going to be our horizontal asymptote. Now, to find these horizontal asymptotes, all we really need to do is remember our rules from pre-cal. So in pre-cal we said if the numerator grows faster than the denominator, then the horizontal asymptote does not exist. If the numerator and the denominator are growing at the same rate, then the horizontal asymptote is equal to y equals a over b, where a and b are the leading coefficients of your numerator and denominator. So we'll say a and b are leading coefficients. So a and b are leading coefficients. If the denominator is growing faster than the numerator, then the horizontal asymptote is y equals 0. Now, all of this stuff growing faster in the numerator than the denominator is really, we only saw it in terms of power functions, so like x to the third power over x to the fifth power. But in calculus, we're going to have to look at just relative rates of growth between different types of functions. So we have on our screen, on your paper, a list of different types of functions who grow from the slowest to the fastest. So the slowest type of function that we're going to see is the natural log function. Then come roots, so square root, third root, fourth root. Power functions, so x squared, x to the third, x to the fourth, x to the fifth. These are generally going to be polynomials. Then we have exponential functions, which is generally going to be e to the x. It could be like 3 to the x power. That's still an exponential, but generally we're going to see stuff like e to the x. And factorials, so stuff like x factorial. We're going to deal a lot with these things later on in the year, but it might show up on a multiple choice question about horizontal asymptotes. Now we have a little star here next to roots, and it says check the power of your variable after you take the root. So if you have something like the square root of x squared, that's really just x, and that's going to grow at the same rate as x. So we have to kind of think about our root before we figure out what's going to grow faster than other ones. So we have a few examples of what these things might look like. So the first two here, the first one, the limit as x approaches infinity of 2x over 5 or plus 5 over 3x squared plus 1. So these are both power functions. So we have to kind of think about which power function is going to grow fastest. Well, this is x to the first power. This is x to the second power. So x to the second power is going to grow faster. So if we think about the rules that we just saw on the previous slide, if the denominator grows faster than the numerator, your limit is 0, which means we have a horizontal asymptote at or not at, but of y equals 0. So there's two ways that AP can ask it. They can ask you just to find this limit, or they might say, what is the horizontal asymptote of the function? They're both asking for the same thing, this limit here. Now 2 looks the same, but we changed our power in the numerator to 2. So the numerator is growing at a rate of x squared, the denominator is growing at a rate of x squared. So we want to think about how they're growing in respect to each other. So they're growing at the same rate. So if they grow at the same rate, then our limit is going to be equal to, and our horizontal asymptote is going to be equal to, the ratio of the leading coefficients, a divided by b, in this case, 2/3. Now this 5 and this 1, if we think about what's going on, make zero difference in the big scheme of things. If x is going to infinity, we're squaring infinity, and then we're adding 5. Well, if we're talking about an infinitely many large set of things, and then we add 5 to it, we're not changing it at all. Right? So if you think about a beach, if you add 5 grains of sand to a beach, you didn't change the beach at all. So that 5 and that 1 aren't going to make a difference. Even if we had plus x plus 5 in the numerator, so 2x squared plus x plus 5. That x squared is what's really driving the force between how fast we grow. So the only thing we really want to look at is the biggest power. So let's look at a couple more examples here. Number 3, the limit, again, we're just changing our power. So our numerator now is growing faster than our denominator. So we can say one of two things here. We can either say that this does not exist, or we can say it's going to infinity. If it's multiple choice, they're never going to have both options, so pick the one that they decide to use. And if it's free response, either of those options would be acceptable. So does not exist or infinity. We can say does not exist because infinity is just an answer. We're not approaching a certain number, so our limit doesn't exist. Because remember, the limit's just the y value that we're getting close to. Now 4 is an interesting problem because we don't have anything on our list of functions and how fast they grow here. This is a trig function. But if you think about what sine looks like, just the graph of sine. And this is a really poor graph of sine, but there's kind of what sine looks like. Sine is always going to bounce somewhere between -1 and 1. Right? It's never going to get lower than -1. It's never going to get higher than -1. So we know our numerator is going to be somewhere between -1 and 1. So that's not really growing at all. This is growing with a power of 1. So that means our denominator here is going to be growing faster than this is going to be growing because this doesn't grow, right? It's just going to bounce back and forth between -1 and 1. So our answer here is going to be 0 because the denominator is growing faster than the numerator. So a couple more examples and then we'll call it quits here. So 5 and 6 deal with that warning that I had about your radicals and your powers. So we can't just think right now that the numerator grows faster because it's a power and this is a radical. If we think about it, if we were able to simplify this, we would get 3x plus 2 in the numerator. We would get the square root of 7 times x plus some other stuff in the denominator. So our powers of x are actually the same here. So our powers of x are the same, so they're growing at the same rate. So our limit here is actually just going to be 3 over the square root of 7. So we have to be careful with our radicals. If this were just the square root of x, not square root of x squared, then our numerator would indeed grow faster. But this is growing at a rate of x, this is growing at a rate of x, so we're going to get 3 over the square root of 7. So if you just glance at 5 and 6, it doesn't look like there's any difference between the two of them. But if you look closer, you can see that number 5 is as x goes to positive infinity, and 6 is as x goes to negative infinity. So this is the only time where you're can potentially get different answers for your left and right horizontal asymptotes. And that's going to come from the fact that the square root here really kind of gives us a plus or minus going on. So the thing to remember is if you have square roots, your answer is going to be either positive or negative based on which type of infinity you are going to. So in this case, we are going to the negative infinity. So our answer is actually going to be negative 3 over radical 7. So if radicals are involved, make sure you're paying attention to which infinity you are going to, because it actually matters with these problems. With the other problems, it's not going to matter at all, but it does with our radicals. So 2 more quick examples, and then we will stop on this video. This one here, we have the limit as x approaches infinity of 5, or x to the 5th over e to the negative x. So we can think about this, since it's e to the negative x, we can really think of this as the limit as x approaches infinity of x to the 5th over e to the x. So we have a power function and we have an exponential function. According to our chart, our exponential function grows faster, so we get a 0 here. On 8, we have a power function x to the 1 over e. 1 over e is just a number, right? It's similar to like x squared or x to the 3rd. Over natural log of x, well, natural log of x is the slowest growing function that we have. So our numerator here is growing faster. So we're going to say either infinity or does not exist. So that's going to be it for this video. We'll see you in the next one.